Here we are going to evaluate the moment of inertia of a triangular area. We're going to do that first about this axis right here, which is the axis at the base, and then using parallel axis theorem we are going to move that to the centroid of the cross section. So as I mentioned before, here the element is first step, right, is to define the differential area element right here. And in this case, we are going to select that again as a horizontal strip. The width of this strip, b, y, it's a function of y, which is equal to b times 1 minus y over h. Right? When y is 0, if we measure y from the base, when y is 0, by is b. When y is h, then by is 0. That's by, and then the width of this differential element is dy. So our differential area element is by times dy. It's equal to b 1 minus y over h times dy. That goes in there. And since we are expressing everything as a function of y, the integral goes from 0 to h, y squared, b 1 minus y over h dy. Now we just distribute the integral on the sum, and we have y squared b dy minus integral from 0 to h of y cubed b over h dy. This integral here is 1/3 b y cubed from 0 to h, and this one is y to the 4th divided by 4 times b over h from 0 to h. This here becomes bh cubed over 3 minus bh cubed, because one of these cancels out, right? Divided by 4. If you do the addition, this comes out to be h cubed divided by 12. So that's the moment of inertia around x1. So that is the moment of inertia around the base. Now what we want is the moment of inertia around the centroid. So in this case we have to use the parallel axis theorem. The centroid of this is at h over 3. So we have to say Ix will be Ix1 minus A times h over 3 cubed. In this case the area is simply BH divided by 2. And so the moment of inertia around the centroid would be bh cubed divided by 12 minus bh over 2 times this is h squared. H squared divided by 9. Again, this is h over 3 squared. The answer becomes, this is bh cubed over 18. But when you subtract it, you get bh cubed over 12 minus bh cubed over 18. The common factor is 36, so this becomes 3 minus 2. And the final answer for the moment of inertia around the centroid of the triangle is bh cubed over 36. So the moment if you had a beam with this kind of cross section like a triangle, the moment of inertia around the centroid, like this, would be bh cubed over 36, which is 1/3 of the moment of inertia of a rectangle of equivalent outer dimensions, right? Remember, the rectangle is bh cubed over 12, and the triangle would be bh cubed over 36. The centroid is at different places, but eventually the moment of inertia around their own centroid is 1/3 of each other. So although you have half the area, you have only 1/3 of the moment of inertia.